Hi, and welcome to SpatialSim, recognizing spatial configurations of objects with graph neural networks. So first we want to motivate this task. So to successfully act in the world, an agent must be able to reason on individual objects and their arrangement in space. So we'll present two motivating examples. Here you have instantly recognized a familiar pattern, a familiar configuration of objects, which is a tower. And secondly, sometimes you have different objects in front of you and you have a reference configuration of objects, and you may want to learn to compare if the configuration of objects in front of you is the same as that of the reference configuration in front of you. So there has already been work on relational reasoning between objects in tasks like visual question answering, and specifically in the clever task where you have sets of objects and questions are asked, relational questions are asked on the objects. The problem is that the relations used in those in this task is those that are labeled by natural language, and they are not expressive enough for our purposes. For instance, they are not invariant to the point of view of the observer. So to tackle these problems, we introduced the SpatialSim benchmark, and our objective here is to learn spatial similarity classes of sets of objects. By spatial similarity classes, we mean that the configuration can be rotated, translated, or scaled as a whole. And to this end, we introduce a set of two tasks related to the motivating examples above. First task is identification, where the model has to be able to learn to recognize a specific configuration of objects with a specific pattern of objects. And comparison, where a model has two different configurations of objects as input and has to be able to learn to say if the two models, if the configurations are similar or not. So features of the benchmark. We are in 2D space and we use symbolic features for our objects. We consider that we have already a perfect feature encoder that is able to extract the relevant objects from the scene. And in this particular setting, we ask ourselves, are we able to learn to identify and compare spatial configurations of objects? So we provide some illustrations here for identification. So here we have 4 samples of our data set. The first 2 samples, which are represented by images here. So the first images on the left correspond to positive samples. And you can see that they are the same objects and the spatial configuration has been rotated and scaled and translated, but it's the same configuration. In contrast to this, on the right here, you have 2 negative samples from the data set where you see that it's the same objects, but their position have been randomly resampled. So for the comparison here, we have 2 samples, and each sample is composed of 2 different configurations. On the left here, you can see that it's a positive sample where the objects are simply, the configuration is similar in the 2 different examples. And on the right, you can see a negative sample where the objects are randomly reshuffled around, but it's the same objects. So the models we use here, we used 3 different GNN models of increasing connectivity in addition to an MLP, multilayer perceptron baseline. So first we use the deep set, which is a trivial GNN where the nodes are unable to communicate one with the other, and the output is done by aggregating all the results from the different nodes. We use a model that we call recurrent deep set, which is similar to a deep set, except that each node has access to global information about the whole scene. And we use also a message passing GNN on an underlying fully connected graph. So this means that each node, so each object, is able to communicate with each other object. For comparison, since we have 2 different configurations of objects as input, we use 2 different graphs and 2 different GNN layers. We use their encoding, their embedding, to generate a prediction for the 2 input configurations. So experimental results. Here on the identification task, you can see on the first line that the MPGNN basically solves the task with a very high accuracy, whereas the less connected variants and the MLP struggle to learn the task, especially as the number of objects becomes larger. On comparison, you can see that the MPGNN here on the first line struggles a bit more to learn the task, has reasonable performance, but is not able to solve the task. And the other models have much lower performance or are unable to perform above chance, which is 0.5. We also provide in our paper different analyses that highlight other limitations of MPGNet and all kinds of models on this task. So to conclude in this work, we introduced SpatialSim, so a new geometrical reasoning benchmark, and we hope to foster further work on geometrical reasoning in the community by introducing this benchmark. And we showed that more connected GNN variants perform better on this task, highlighting its relational nature. So further extensions, we may want to learn the object directly from a pixel setup using all kinds of different methods that have been developed recently in the literature. And we may want to also incorporate this into an imitation learning scenario where an agent is trained to reproduce spatial configurations of objects that is presented to it with blocks that it has in its own hands. So thank you for listening, and for more details, please take a look at the paper.